Hello, hello, Mofi here, and welcome to Teaching Studies once again. I have Nick here with me.
Hello.
And Nick, if you could tell us what you're doing today.
Yeah, so we finally wrapped up all the math behind what's going on in these neural networks, and we're finally going to be able to move along to our next chapter, and we're going to do some image classification stuff.
Okay.
However, before we completely sweep the math under the rug, I'm going to give you a little pop quiz.
Oh boy, I don't like the sound of pop quizzes.
Yeah, so if you're someone that doesn't care about math, feel free to skip ahead to when we stop using the iPad. And if you do care, maybe take this as a time to pause the video once asked the question and try it out yourself.
Well, it's a live stream, they can really pause the video.
Well, yeah, it's true. In YouTube, if you're watching this later. All right, so I'm going to draw a network for you.
Sure.
And your goal is to give us the gradient of one of the weights that I tell you.
Oh boy.
And this is going to be a network we haven't seen before. So here we go. We'll start with our x. We're just going to have one input, one output.
Okay.
And I should draw that down lower. X. And we don't have to worry about activation functions. We're not going to use bias. It's going to be pretty straightforward. So we're going to have this one. I'm just going to label the weights as 1 and the hidden layers as 1, 2, 3, or whatever.
Okay.
I'm not going to put a W in front of it just for simplicity's sake. So we're going to have one node. And this node is going to connect into 4 nodes. So node 2, 3, 4, and 5. And then those are going to go into 2 more nodes, 6 and 7. And then that's finally going to go out to our Y.
Okay.
So we'll just connect all these up.
Make it more complex, why don't you?
Nice mess. All right, and then this is going to be, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Sure.
All right. And then, so I want you to find the derivative in terms of this first weight.
Derivative of what?
Okay, so we have our error function, right? So we're just gonna, I'm not gonna actually make you like derive and get all the terms. I just want you to write out all the partial derivatives. So if we like look at this weight 14 right here, the derivative with that, we would want to find dE, dW14. And then all I need you to find is the answer for this would be dE, dy, dy, dW14. That's all I need. Does that make sense?
Okay.
So we're just going to try and turn this derivative into its partials.
Right.
Right. So to start it off, we're going to want dE, dW1. And I'm giving you the pencil.
Oh boy.
It's all you.
Okay.
And I'll definitely be helping you along the way.
Yeah, please do. Okay.
So where do we start?
I mean, the very first thing is that we definitely start to like backpropagate all the way from there to all the way there, right?
Right.
So, so this one will be the first term.
Mm-hmm.
Okay. So my handwriting will probably be better than yours, though.
Probably.
And then I'm looking for like what chain I can like come back to this for, right? So what will
Right. And some things that we learned in the last time is that so for this 14 weight, or let's talk about 6. 6 only goes through this hidden layer 6.
Right.
But when we're talking about 1 here,
one goes
it
through
can
everything.
go through everything.
Right.
So
So you just add all of them up,
right.
all the chains.
Right.
So basically, you do. I'm gonna take like a different color pen here. Let's say I take a lighter, I'll take a gray so that it's not too visible. So you take this one. You can 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 take. I already missed something, right? So
Yeah,
you have
literally every line on there.
so
It'll take.
so it'll take all 8 of them. So you add
Right.
all of them up.
Yeah.
Right? Okay. So I'll go back to my red. So the first one would be, so you do this one, then I can do the 14 one. So it's going to be, oh, I can directly, yeah, I can do DY over the W14.
Right, and then I'm gonna stop you here.
Okay.
We have to remember that once we like the intermediates, we can't really affect the other weights. We're only focusing on the change of this one weight.
Right.
So going back, we're only gonna most of the derivatives are going to be in terms
on the layers.
of the,
Right.
Yeah.
Yep. No, I remembered that part, but I forgot that part. So I call it just 6, right?
Yeah, or DH6.
Oh yeah, H. Yeah. And that one then is gonna be, that is depending on this one, right? And that is depending on this one.
And then, so when we're talking about this,
Yeah.
So we're talking about this, so DH6, and you said it's dependent on this one, right?
Yeah. Well, one of the chains.
And that's good, but we need to also consider these other.
Yeah.
And if you remember last time.
Oh, that's where it's going to be all added.
Right.
Yeah. Instead of okay. Yeah. Right. Okay. So we can do it here, and that is going to be the H6 on H2 plus, I think, H6 on DH3.
Yep.
Plus the H6 on the H4, and I see where handwriting is really bad here. The tip is very slippery. It doesn't want to grip. DH6 on DH5, and that is basically that. And then all of this whole thing. Now I'm in a conundrum. How? Because all of them then depend on this DH1, right?
Right. So try and think of it as this term right here. We can kind of just pretend like this is DH6 with respect to the derivative of just this entire row.
So that entire row being this.
Right. So here we can just do if we can just multiply this by DH DH1 over DH. Wait, I think we missed.
Oh boy.
Missed a step.
What did we miss?
So when we were talking about
dy was supposed to be part of those two, right? It was made up of 6 and 7.
Right.
Okay. Yeah. Well, luckily. So you're gonna move this for a second. Well, I should probably not move it like that.
It might be easier if instead of writing them like next to each other, when we're talking about a column of these hidden layers, maybe just write them like on top of each other.
Yeah, that's you know what? Forget it. I'm gonna just erase. I'm gonna erase. Right, try to write it cleaner this time. You know what? I'm gonna just take this. This is way too big. And to resize this. Okay, so that I can have more stuff fit.
Beautiful.
And okay, that is done. Take this, move it up. All right.
All right, we
I'm
got
in
this.
business.
Round
So,
two.
round two. Okay, the very first thing would be you have your, well, I forgot the very, okay, I still remember. dE over dy, and now dy would be in terms of these two things.
Right.
So I can say dy is dy over dh6 plus, oh, I'm still doing it side by side. That's not do it bottom.
Well, so you can put that back, and then I would just do the dy d7 underneath it. But for now, we can just because I know what's going to be happening ahead. Let's just go like this and ignore the 7 one for now. And then multiply this by the 4.
Right. So that, okay, got it. So this is gonna be dh6 over dh2, and then I have like bunch of the pluses.
Right.
So these are all plus. So dh6 over dh3 plus dh6 over dh4 plus dh6 over dh5, and then each of them are also multiplied with the dh1 thing, right? So this one is multiplied with dh2, dh1. This one is dh2, dh3,
Yep.
dh1, oh my god, dh4, dh1, and dh4, 5, dh1, and this has been too big, so I'm gonna be, what I lack in, I can just make them smaller. That way I can fit both of mine right there. All this less readable, but it's fine. I know what is under there. So okay, so I did all that. And then we have individual ones. I shouldn't have made them smaller just yet. But then the dh1 then is actually directly controlled by that. So I can say, for this one, I can say...
Yeah, and so you could either multiply all of those by that, but then that's the same thing as just multiplying this entire block by that. So.
No. Have you done this before?
Yeah.
Oh, okay, that's why. Okay, got it. And multiply the entire thing by, I can say, dh1 by dw1.
Beautiful.
And do the same thing for h plus, do the same thing for h7.
Right. Which I think you got the point.
Yeah. I mean, this part will say the same, so I can do it. It's fine. Yeah. Okay. I can just do this and say copy.
Wow, what a beautiful way to do this when we don't have to actually copy and paste on a piece of paper.
Yeah, so I can say dy over dh7 and multiply this whole thing by dh1 over dw1.
Right, and then instead of dh6 here, those would all be dh7.
Yeah. Well, our audience got it. They got it.
They're smart.
Okay, there you go.
All right, that wasn't too painful.
It was.
It wasn't that bad.
Right. That's why I trust computers to do it. I don't want to do it manually.
Right. So now we can completely throw all this knowledge away and push forward with the more interesting things. The rest of these videos should just be mainly fun little projects and actually learning how many layers and all that kind of fun stuff.
All right.
So let's go to the code.
Let's go to the code. We are on the right screen, hopefully. Yes, we are. Then I can just like swipe. Bam, I'm in the code.
Beautiful. And
I'll bump up the font just a bit for anyone watching on a smaller device. And I'll probably kill this. I have more space here.
I'm going to go through here and delete a bunch of code.
Did it finish training?
I think so.
Okay.
So I'm going to delete this, right? Yeah.
But like that training, we didn't even test if it did any better or worse.
Yeah, we'll see.
It's okay. Whatever.
So just ignore everything that I'm doing right now.
So while we got started, the example, we're just like testing out the example with a different set. I mean, very wise to do 10 minutes before actual demonstration, but hey, we like to live life dangerously if you have known us.
All
for a
right.
while now. Okay.
So here we go.
I mean, are you sure it's the same thing that we started with?
Yeah.
Okay, cool.
Pretty sure.
I mean, I could have just done a git reset hard and just.
It's fine.
Okay.
Okay. So, what we're doing, we're trying to classify handwritten digits. So
That's the classic problem.
Yeah, it's like the hello world of computer vision, So the goal is we write some numbers and it can guess what the number is.
Mm-hmm.
And this is a little bit different.
And anyone, before you go any further, anyone wants to like try this thing out themselves, you can find this URL. This is the URL, github.com/bordacus1/webinar-course-example.git, or just get rid of the git if you want to find the website itself. And it's part 5, if I'm not mistaken. Yeah, so you can find all the code there. And with that, I'm going to let you get back to it.
Cool. Okay, so with our regular neural network, actually, do we want to pull the iPad back out?
Yeah, sure.
I think it makes sense to draw some of this stuff out first.
Okay, iPad, let me just see if it's still connected. It is connected. Excellent. And it's not. What the hell? I'll do this again. I don't know what is happening. Hold on. Reflector is on. Oh, I disconnected from the internet. Bam. Okay. We're all online. We're all nice and beautiful. We are connected. Like that. That's it.
All right. So when we had
hold on. Give me one second. I'm gonna just push it to the left side so that no one gets cut.
Beautiful. So we had a neural network. We had a couple inputs, and they go into like this neural network. This is a bad rendition of a neural network, but we have these two x's and we get a y. But in our scenario, when we want to pass an image through, like how would you think we would do that? How do we put an image through this network? How do we turn it into something that the network can actually understand?
I mean, the whole image is just like a bunch of pixels. I mean, or like sending all of the pixels individually would be too much. So I'm not 100% sure what would be.
That's exactly what we're going to do, actually.
So you're going to send each pixel like as an individual input? Mm-hmm. Okay.
So we're the data set that we're going to be using, MNIST. Each image is 28 pixels by 28 pixels.
Okay, that's not too bad. I'm thinking about like actual like image from my phone. That's like 4,000 pixel by 3,000 pixel. That's
right. Most neural networks always squish it down to something fairly small.
Like
so
50,
you
like less than 250 pixels and such.
Right. Yeah, I think most of the state-of-the-art stuff for classification they shrink it down to like 224 by 224 pixels. MNIST is especially small just because we're just going to have like one number in there.
Mm-hmm.
So this is what our image looks like. We can like just flatten it out into
row side by side. Put the rows next to each other. Okay.
And then so we just have like what is that, like 700 something? What's 28 by 28?
So 30 times is 900, 20 times is 400. So it's between 400 and 900.
Yeah, I think it's 700 something. So we're gonna have 700 something inputs, and it's gonna be going into our fun network. And then however many hidden layers is something that we'll play around with, and then we'll end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs.
Okay.
And each one of these 10 outputs represents one of our classes.
Mm-hmm.
So with our digits, all of our classes are 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what each one of these will represent.
Okay.
And so if you remember last time when we did the negative and positive classification,
right,
we had a vector or like an array, and if it was negative, it would be that. If it was positive, it would be that.
Right.
Right. We're going to do something similar with these numbers, except this time this array will be 10.
Because you have 10 numbers,
And
yeah.
if we want it to be 6, the sixth element in the array would be
Well,
1.
7th.
Or yeah, 7th, yeah.
Array starts at 0. Okay. Also, the number was 784.
784.
Right.
Thank you. Okay. There we go.
Okay.
So yeah, that's the
So 784 input, 10 output,
and then
how many hidden layers?
This hidden layerness, that's what we can decide. That's up to us. We'll talk more about that when we get to the code. But those are like our constraints. We have 784 inputs and we have 10 outputs, and then it's up to us what goes on in the middle. And that's why they call them hidden layers. They're not really hidden. That's just what.
It's just like classic computer science bad naming problem.
Yeah, that's just like the black box that we're deciding on. Okay, I think that's all the prep you need to do. You can go back to the code.
And we're back.
Wow, how easy. All right, so inside of Keras, they actually give us some sample data sets to work with, and MNIST happens to be one of them. So in order to get these images, we just do MNIST load data. It's easy as that. And it already splits it into an X train, which are all of our training samples, and Y train, those are all of our predictions, and then X test and Y test, which is just another separate set that we can use to actually test the accuracy of our model later, things that it hasn't seen before.
Right.
And in the beginning, we're just converting it to float because they're the way MNIST is built, instead of it's 0 to 255. So those are ints, and if we were to divide them, they would just be 0 or 1, depending. So we're going to convert it to a float so that we can divide the pixels by 255, so we can get them down to be 0 and 1.
So it's basically just threshold then, right?
Right.
Okay.
So yeah, we're converting the pixels from being from 0 to 255 to between 0 and 1 before we send it through our network. And then another thing we do, we're converting the class vector matrices into like a one-hot encoded. And the one-hot encoding is what we saw on the iPad, where it's like a row vector, and there's 10 items in it, and if it's 1, that's the class that we're predicting. Yeah. Whereas MNIST, they just give us the actual number.
I see.
So like you give it there's an image, and then the Y train would just be 4. An image, the Y train would be 1. An image, the Y train would be 3. And we're just turning that into this.
Okay.
So 4 would be 0, 0, 0, 1, 0. Does that make sense?
Yeah.
Cool. And that's what this 2 categorical 10 being however many classes we have. And then we're just doing another keras.sequential. That just means we can keep popping more layers onto it. And so our pixels are 28 by 28 pixels. Most like color images, there's a third channel for red, green, and blue. But we only have one color, which is black and white. And so it's just 28 by 28. So we're starting off with this flatten layer. And what that is just taking this 28 by 28 array and it's flattening it out like we saw.
Just like one long array.
Line. And then that we can easily feed into this dense layer, which is the fully connected stuff that we've been working with. And we're using the ReLU activation. And we have 3 layers, 128 by 128. And the output is 10 because we have 10 classes. And then again, it's the softmax, which we saw before, if you remember that. It's good for like categorical stuff. And we're compiling our model with categorical cross entropy, which again we saw last week with, that was, again, the typical loss function we use for when we have classes versus the mean squared error for the other ones that we've done in the past. And then we're just using this stochastic gradient descent with a learning rate of 0.1.
Okay. Isn't that too big? Usually we use learning a much smaller learning rate before.
It's something you play around with.
Okay.
If it's going too slow, you can bump it up, and then if it gets really funky, then bump it down.
Okay.
And in the future, we'll learn about other optimizers that play around with the learning rate as it's training. And then the metric we care about is accuracy.
Okay.
And that just will print out. Normally, whenever we run a keras thing, it'll just give us the loss.
Right.
This will give us the loss and the accuracy.
Okay.
And then we're just fitting like we normally do. This is an unseen thing that we haven't seen yet, batch size. And the reason why we have batch sizes is because our MNIST data set is 60,000 images. And if we try to load all of those into memory at once...
Probably be okay still, but really take a toll. Yeah.
Yeah.
I mean, these computers are like pretty beefy, right? So.
Yeah. I'm not sure what... I feel like it's a lot.
I mean, 60,000 images that are only like 28 by 28 pixels. Yeah. It's not too bad. But again, still, it's gonna... It's not Chrome bad.
Okay. Yeah. It's a lot to fit into memory, and then you have to run through
it.
Yeah, so instead of pushing it all through at once, most people, they break it up into batch sizes. So we're only putting through 128 images at a time.
So for each epoch, you're breaking the 600 images in 128 chunks. So each epoch will be then like close to like, I don't know, 5,000, not 5,000, sorry, like 500 different steps. Each epoch is broken down, right. Whatever, 128, 6,000 out to it.
So normally whenever we compute the gradient, we take into account every single training example.
Yeah.
Where here we're only using 128 of them, and then we're doing that multiple times and then adding them together to.
Okay. Yeah. So that's about like 470 times.
Yeah.
Do it. Okay. For each. Okay.
And then we're doing 15 epochs, and then we're evaluating it and printing out our score, and then we're saving the standard keras file, which is like .h5 that has the model structure and model weights, and that we can use to reload, so we don't have to train it every time we want to use it. And then we're also converting it to a TensorFlow.js model.
Okay.
And that'll make it really easy for us to load it into a nice little web app that we can like draw numbers and test stuff like that. And before I run this, how do I see your files? Your VS Code is set up different than mine.
Yes.
I'm going to rename this to something else.
Oh, because that's the one I created.
Yeah.
Yes.
And then make it happen.
All right. So I'm going to do a quick Python MNIST example pi. It's warming up.
Hopefully it'll work because we changed stuff. And okay. So there, it's starting out with 85, 95, 96, 97 accuracy, which is pretty good.
But accuracy on that given test data.
Right.
Okay.
And then we had a 97% accuracy on the 1,000 test examples that were held out. And then if you run yarn start or npm,
let's just do yarn first to see if anything is missing. First download, nothing was missing, because again we tested it like half an hour ago.
Right, and then so yarn is just like for those of you who don't know Node and stuff like that, it's a package manager.
So this is where I draw stuff.
Right.
And I'll try to draw it too. Well,
it's working.
Don't get too happy, because like when I tested before, half the things didn't work. So I'm gonna try to draw a 5. It's a beautiful 5 if I ever saw one.
Wow.
Okay. Okay. What if I do a 4? Okay. What if I try to do an 8? That's not a good 8.
Ah.
Okay. What if I do a 6? Huh?
Okay.
I had trouble with 7 and 1, so I'll try that next. Yeah, that's what. Okay. I'll try. What is a 3 supposed to look like? That's a nice enough 3. Still
Okay.
3. But let's try to draw a 1. I couldn't draw a 1 for the life of me last time around. And this is not even a good 1. Okay, this is still a 3. 9. Okay. Okay. 0. 0 is a tough one. He's probably not going to get it. Oh, yeah. It loves 3. Like everything is 3.
Yeah.
Anyway, okay.
So this model we used was just using these standard dense layers that we're using.
Okay.
And whenever you think about like where these values are, if they move around a lot, it's gonna kind of affect. I should probably draw some more stuff again.
It's all again gone.
Yeah.
And the Wi-Fi, I don't know why an iPad just like decides to disconnect the Wi-Fi every time I like. Probably trying to save battery and stuff. But it's annoying nonetheless. 2, 2, 6, 2. Okay, I'll also move it on this side. Okay, there you go.
All right. So this is our image, right? And in the MNIST data set, it's like pretty, like, I guess, sort of fixed. Like all the numbers are like centered and like take up a certain amount of area. So when we feed it through the network, it can start seeing like, okay, like 6, it normally appears around these sort of pixels because those are the pixels that are getting fed through. So if those pixels are lit up, we can kind of assume it's probably a 6. However, if, so say here's our kind of cloud that it's sort of expecting.
Sorry, my speaker got, my cable got stuck under the chair.
Oh no.
Yeah, it's hold on, it's okay.
Just lift your chair up.
I know, but I can't even get up because I'm stuck on the chair. Cable is stuck. Okay, there you go. I'm good. I'm free.
What a mess.
Boy. Okay. All right, I'm back. Here you go. Let's go.
So our network is kind of expecting this sort of like cloud of like this area where the pixel should be. And again, that's kind of like right here. But if we were to draw a beautiful 6, but it was right here, it's not really lighting up any of those nodes that we want it to light up.
Right.
And this is something we're going to be talking about in the next episode. And this is where a different layer type comes in, and that layer is
Convolutions. I read your blog post.
Oh, yes. So if you read my blog post, you'll know that a convolution it's a smaller sort of window that, let's say, looks like this, and it gets slid over the image, and then it classifies there. So it kind of, this, when we're using a regular neural network, it's very sensitive to translations. But if we're translating the box around the image, then it doesn't really matter as much where it is because the kind of cloud that we care about isn't like localized in that one spot. And normally with convolutions, we'll be talking about it more later. It's not expecting like a 6. It's expecting kind of like an edge or like a smaller breakdown, and it kind of adds up. But we'll talk about that later, and we can see if we can if we try out the
Model 2.
Yeah, it might work. I didn't test it yet, so we'll see.
On your JavaScript code.
There it is, source index.
And this Model 2?
Yeah, let me go ahead and save that.
And close it.
Yeah.
And yarn start again?
Yeah. It should have auto redid it. You probably didn't need to restart it,
No.
but
You always restart.
all right. Now, hopefully, if we write it, it might crash, but
0.
yeah, it crashed. Oh, yeah. So there's going to be some more stuff that we need to change in the JavaScript code,
Which we didn't. So
yeah. So I'm going to walk us through the JavaScript code anyway. But
I did redo it.
how do I close the editor? All right. So I'll run through this code because I think it's important to kind of like see what we're doing in TensorFlow.js to get it to work. And this is using React, so it can be a little foreign to people who haven't dealt with that kind of stuff yet. So we have this app function right here. And this function gets reran anytime our state changes. And in this example, we have model and prediction are our state. Prediction is our prediction, and model is the model that we end up loading in. And then we have this a reference to our canvas element, which is all the way down here at the bottom. And it just has like a 1 pixel border around it so we can see it.
Right.
And we pass this ref to use canvas brush thing, and that is what turns our canvas into kind of like a little paintable area. And the code for this is in another file. And then it gives us back this canvas brush so we can use that to clear it with this clear button down. But that's not too important. Then we have this use effect, and everything inside of this effect is only going to get run on the very first time we load the page. And that's kind of important because app is getting rerun a bunch of times.
Right.
And we don't want to load the model every time something changes in the state. So we're loading the model, and we're using this tf.loadLayers model, and then the public URL for the app, the MNIST model, and the model.json that is inside the MNIST model. And then we're setting the state to have this model. And then we're serving this. So if you could tell, it was like on localhost 3000 or something. And that's because if you don't, then there's like a lot of CORS problems from just statically running it on your desktop. Okay, so then here's where the magic happens. This is all the TensorFlow.js code. This predict function gets called whenever we hit the predict button. So the first thing, you'll see this tf tidy, and then this callback arrow function. And what happens in tidy gets disposed of. So anytime we're creating these tensors, they might stick around in memory, and they can be kind of big and cause memory leaks. So I think people normally put them inside of this tidy function, so they just get disposed of automatically. So the first thing that we do is tf browser from pixels, and we pass it the reference to our canvas, and it gives us back the image as a tensor. And a tensor is just kind of like a fancy way of saying array or an array of arrays, but it's specific to what TensorFlow needs to process our image. And I think like technically, like a tensor is just kind of an abstraction between a vector and a matrix. Where like a vector is just like a single row matrix.
So a tensor, you can have both, but call it under the same name, and just understand underneath what to do with it.
Right.
Okay.
And then we have this image, and we're subtracting it by 255 and dividing it by 255. And the reason why we're doing that is, again, we need to divide it by 255 to normalize it down to the 0 and 1.
Right.
But the reason why we're subtracting it and then dividing it by this negative is because our model expects 0 to be nothing, and then 1 to be our pen color.
Right.
Which would mean the background should be black and the pen should be white. So we're just kind of inverting the image to be vice versa. And then our image that we get is 280 pixels, and it needs to be 28. So we're just scaling it down.
Okay.
So we get this scaled image. And then the image that we have is actually RGB, red, green, blue.
But it's all
So we
black.
have 3 channels, so we need to turn it into black and white. And a simple way to do that is just taking the mean of the third axis, which should be 2 because it's indexed by 0. And that will end up being like this. So 255 plus 255 plus 255 divided by 3 is 255. And the same thing with all zeros.
Mm-hmm.
And the reason why we do the mean and we don't take just the top, we could just take like one of the things if it's in black and white like this, but if we were using a different pen color like red, then it might not be picked up as a color. And then when you're turning a grayscale image into black and white with other types of networks where it's not just so cut and dry black and white, you don't normally just take the mean because the mean is 30%, 30%, 30% essentially for each color, or 33%, sorry.
30.3.
Yeah, 33 repeating. Okay. Yeah. But whenever we look at colors, if we look at green, green kind of has like a lot lighter of a presence than like blue or red. So if we were to just like take a picture of like some grass, the picture might look super, super dark because the green is weighted equally as like the red and blue. Okay. So normally people use something similar to this, is like 0.2 red, a lot of green, and then reduce the weight of the blue. And I have a link to the Wikipedia article that talks about like the different grayscale conversions. And that's something like if you've used like Photoshop before and you're like changing an image to black and white, it'll allow you to like actually like specifically choose it to make it look nicer. Anyway, I diverge. And then we're expanding the dims, which is expanding the dimensions. We're essentially just putting our 28 by 28 pixel array into another array because our TensorFlow model is expecting batches. So we could pass through like 5 images at a time, and it would give us 5 predictions back. We only have 1, so we're just going to put it in an array, so it's the first. And then we're just getting the predictions. This data sync just gives us the data. It makes it calculate it, and we bring it out. Yeah, there's predictions. And again, this isn't another tidy, just because we'll be throwing away most of this stuff. And then we're doing getting a 1D tensor array of the predictions, and we're doing an argmax. And what argmax does is it just gives us the index of the highest value in the array. Okay. So like
because like every time you're putting there is a chance that TensorFlow can say this looks like a 3, also a 6, a little bit of 7, and you want the top highest accurate like confidence one.
Right. Okay. And even then it's if it was like we're one hot encoding it, right? So if it was 3, it would be 0, 0, 1, 0, 1, 0, 0, 0, 0. So we want to find the index of where that 1 is. Okay. So that's like what argmax
okay. Does. So not what I was saying. It's a different. Okay, cool. Yeah.
Okay. And then we're just setting that prediction to the state. Okay. And then, so the reason why it failed for us when we tried to change it to convolutions is because convolutions expects
a different dimension of array?
Yeah, 3D dimension of the array. So right here, we end up with this 1 by 28 by 28. The convolution expects another channel, the 3 or 1 in our case. So we just need to push on another dimension, and then it should work.
Okay, I mean, cool.
How do you feel?
I gotta probably play with it a little bit more. So I'm gonna probably clone it and try to change stuff around to see if things do work. But interesting stuff.
Yeah, and then next week we'll probably do the exact same example. But we'll talk a lot more in depth in convolutions and see how the accuracy is a little bit better.
Excellent. Yeah, so thank you so much for joining us this week. And hold on, just before we finish, let's switch to this one. All right. So thank you so much for joining us this week again. And hopefully next week, on my side of cloud native things, we'll get started with Kubernetes. just like because we've done enough Docker, and I think we're going to use
Done
some.
with Docker.
Not done with Docker. Docker is a big behemoth. But we have done enough containers. Docker is not even the right word anymore. So we have done enough containers. We're going to build something with Kubernetes next. And I know we have done Kubernetes a little bit, but it's just like ad hoc and jumping really deep into without understanding what's going on. So you're going to probably like understand the whole purpose of Kubernetes. Not whole purpose, some purpose of Kubernetes and how it makes things a little bit better.
Wow, look at us just starting new chapters at the same time.
Right? Like I planned
Beautiful.
this. I planned
Wow.
this. So yeah, so see you next week and until next time.